Hi, everybody. Thank you very much for coming. My name is Rahul Pathak. I'm the Principal Product Manager for Amazon Redshift, and I'm here with Anurag Gupta, who's the GM for the service. So today we're going to dive fairly deep into some best practices around Redshift. We'll get into a little bit of the internals, and then you'll also hear about a couple of new features that we've been working on that I think you'll be pretty excited about. And just a quick show of hands, I'm assuming everyone here is using or has used or is familiar with Redshift. All right, so that is awesome. And so let's get started. So the architecture of Redshift will be familiar to you. I just want to put it up there briefly so we can just level set, and then we'll drill in from here. Essentially, you're familiar. It's a clustered system. We've got a leader node, which is your SQL endpoint. Compute nodes where your data is stored. It's columnar data. Query processing takes place on the compute nodes. We can ingest in parallel from S3, from DynamoDB, or from EMR, as well as from any arbitrary SSH connection. So if you want to copy in parallel from a database that's on-premise, you can set it up to accept inbound SSH from the compute nodes, and we will copy that data over in parallel. It saves you a round trip to S3 on the ingest side. And as you all know, we have two hardware platforms. There's the DW1, which is our hard disk drive platform. And we've got the DW2, which are the SSDs. And we made a recent expansion in maximum cluster size. So you can now have 128 compute nodes in a cluster, and that takes you up to 2 petabytes of compressed data in a single cluster on the DW1 platform and 326 terabytes on the SSDs. And so let's dive a little bit deeper into the architecture and look at what's actually happening on the compute nodes. So on the compute nodes, you've got multiple slices per node. Now, a slice maps to the number of to a core. So on the DW1, the XL platform has 2 cores. There's 2 slices on it. The 8XL instance has 16 cores, 16 slices. Similarly, on the DW2, there's 2 slices on the large and 32 slices on the 8 extra large. Now, a slice is significant. Each one of them is dedicated a certain amount of CPU power, a core, it's got RAM, and it's got disk allocated to it, and it's a thread of execution. So each of the slices processes queries in parallel. If we have to move data between slices to do a join, we will ship that data between the slices automatically and transparently. But this has an implication on ingestion. So a copy command in Redshift is just a query. And so we recommend, as a best practice, you all know this, ingest using copy. It's parallel by default. You can always do inserts and updates over JDBC, but it is slow, especially if you go single row. Redshift has a relatively high fixed commit cost overhead, so if you're only inserting a single row, that commit's going to feel expensive. And so if you do use JDBC or ODBC, batch your inserts so you can amortize that commit cost. But when you're using copy, each slice will ingest a file at a time. And so if you only have a single input file on S3, only one slice will be ingesting data. And so if you think about a 16-slice DW1 8XL, this can ingest data from S3 at 100 megabytes a second. But if you only have a single input file, you'll just get 1/16 of that capacity, so just over 6 megabytes per second on ingest. And that will not scale as you add nodes. So input file splitting is a big part of driving performance. And so when you want to maximize your load throughput, we recommend having at least as many input files as you have slices. And so with a single DW1 8XL, you need 16 input files on S3. Each slice will then load a file simultaneously, and you'll get the full 100 megabytes per second load throughput that's possible. And this scales linearly. So we've actually done tests on 100 node systems, and we can reliably ingest a terabyte of data in about 129 seconds. And that's not even running as fast as is possible, so you can get tremendous load throughput, provided you parallelize correctly. One other pointer here is make sure your individual input files are individually compressed. Basically, if you're loading at 100 megabytes per second, at 4:1 compression, you'll be able to load 400 megabytes of your own data every second. So compression is a best practice, and that's how you'll maximize the throughput of the system. So a couple of things. When you're ingesting, this sometimes bites customers. Redshift does not enforce constraints on primary key columns. So you can define them, but it will expect you to have taken care of uniqueness as you ingest. And so if you load the same data multiple times, Redshift will happily load it. It won't complain to you, but the optimizer will assume, because you defined a primary key on that column, that the data in there is unique, and this can create strange results. So if you ever see a pattern where you get a different set of results when you query a table versus querying a view on that table, check your primary key columns for uniqueness. It's very important if you define them to make sure your app takes care of that. Another thing to keep in mind when you're ingesting from S3 is to use manifest files as a best practice. This allows you to specify exactly what the cluster will load. And it's a JSON manifest file. It lives on S3. You provide it as part of the copy syntax. And you have the ability to control what the cluster will do if it can't find one of those files. So in some cases, you can choose to stop the entire load. Or you also have the option to proceed and skip that file. So we have customers that might ingest hundreds of thousands of gaming logs, and they don't really care if one of them is missing. They have the option to skip it, but at least they know that it happened. And if you're using S3 in the US standard region, this will protect you from eventual consistency, which can sometimes create issues where you think you've written a file to S3, but when the cluster goes to ingest it, that file isn't seen. So manifest files help you deal with that. One other pointer, and we see customers skip this fairly often, so it's very important to keep your statistics up to date. Redshift has a query optimizer that will rely on its estimates of the cardinality of the columns in your cluster to generate efficient query execution plans, things like which order to join tables in, what data to ship where. It's all hinges upon having accurate statistics about your data. And typically when you're ingesting with copy, copy will automatically update stats. However, it often does more work than it needs to because the columns that matter the most to your statistics are your sort key columns and your distribution key columns. And so one way to squeeze a little bit of extra performance out of ingest is to turn off automatic stats updating and just analyze your sort and dist key columns after every load. And that can create some perf gains for you. But statistics, it's very important to keep these current. And in a similar vein, compression, we've talked about it, it's a good thing. You get more data per read, per ingest, per network transfer, and it lowers your costs. And so you can run smaller clusters and drive higher performance. In general, it's a good thing. And copy, again, by default, will sample data, run it across all of the encryption, all of the compression algorithms that we know that are implemented in the cluster and pick the one that saves the most space. And it can sample up to 100,000 rows at a time when doing this. Now, this is a good thing, and it will only do it on empty tables, and then subsequently will use the encodings that's been generated. So that's great. But if you have automated, repeated ETL processes where you might load a staging table, or you might drop a temp table, recreate it, automatic compression is just an overhead, especially if your data looks the same hour to hour or day to day. So turn it off and just pick the compression, define it as part of your DDL when you create that temp table, and you'll save yourself sampling time on repeated loads. So another way to squeeze more performance out of ingest. Now, compression is generally great, but one pointer to keep in mind is that occasionally it can work against you. And so you have to be careful when compressing sort keys. So sort keys are great. We like them. Your data's sorted. You can use our zone maps to skip ranges that don't matter for your queries. But often, say you have time-based event data, you're an ad network or a mobile gaming company, you might use date as your sort key, which is great. It compresses extremely well. And say you had a refer string as one of your data columns, that might not compress as well. And so in the case of your sort key, we might have 100,000 rows per sort key block. And so if we identify that we have to do a minimum of a read of a block at a time, and a block is a megabyte in Redshift. So say we read and we decide that your data exists somewhere in the first block of the sort key. That's 100,000 rows potentially in the sort key offset. And if you get much better compression than you do on your data columns, you'll read way more rows than you have to on the data blocks because you have to read 100,000 offsets. And so if you inspect your data and you find that your sort key columns compress significantly better than your data columns, you might want to think about disabling compression on those sort key columns and look at the performance that you get. Now, if you're running a very compact schema and you've just got a bunch of ints, this won't be a problem. But we often see a combination of just sort of more log-type data brought in conjunction with sort key data, and this is an area where you can drive higher performance. Another big thing in Redshift is, yes, it's a columnar system, and that's great because only the columns that matter for queries participate in those queries. But your columns should be as narrow as possible. Essentially, whenever we have to allocate in-memory buffers to deal with queries or ingest, we allocate the space that's used in the column definition. And so if your columns are varchar max, we're going to allocate 64K for that column, even though it contains much less data. And this leads to inefficiencies because we can only fit fewer rows into memory. Your queries are more likely to spill to disk, and it's just wasted processing power and memory allocation that's not working in your favor. So please keep your columns as narrow as possible. You'll maximize query performance that way. So we talked about ingest, squeezing performance out of ingest. We've talked a lot about Redshift and security, and we've done a lot in this area. And I just want to walk you through the details and how you can run end-to-end secure in Redshift. And what I mean by that is, starting from your source files on S3 all the way up through the pipeline to your queries, you can have that be encrypted and secure and auditable. And with Redshift, we've gone through a number of certifications for SOC 1, 2, 3, PCI, FedRAMP, which is the federal government standard. We've got HIPAA and healthcare workloads running on Redshift. And I just want to dig into all of these pieces so you can see how they work and implement the architectures and policies that you need for your organizations. So starting with source data, you can use S3 client-side encryption to encrypt your data files as you put them onto S3. We have SDKs for Java, Ruby, and .NET. We use an envelope encryption strategy, so there's an encryption key that's used to encrypt your data. This is the envelope key. The envelope key is then encrypted with your private key, and that encrypted envelope key is stored in the metadata of the object. And then when you're ingesting data into Redshift, we do this process in reverse. So you provide your private key as part of the copy command. That then reads the metadata on the object, decrypts the envelope key, and then the system uses that envelope key to decrypt the data payload. Our ingest from S3 is done over SSL connections. So you've got control of your keys at source, encrypted data onto S3, over SSL into Redshift, again, with you controlling your keys. So you've got a secure chain on that side. Next step is securing your data at rest. So we support hardware-accelerated AES-256. There's about a 20% encryption overhead in terms of performance. It can peak higher. So something to keep in mind when you choose to enable this option. And Redshift is MPP, so if you want to run encrypted and not have a performance penalty, you can always add 20% more nodes to your cluster. And for well-distributed workloads, you'll get near linear back to normal performance. So we use a multi-tier key-based encryption model in Redshift. Each block gets its own individual, randomly generated AES-256 key. That's used to encrypt that data in that block. This prevents block splicing. And then those block keys are encrypted using a database key that's just kept in memory on the cluster. And so essentially you have block keys. The block keys are encrypted with a database key that's in memory. That database key is persisted off database, and that's encrypted using a cluster key. So it's only persisted in encrypted form. And the cluster key itself is encrypted using a master key if AWS is managing your keys. And Redshift also integrates with the new key management service that Andy talked about. But you also have the option to use an on-premise hardware security module, or HSM. We support SafeNet Luna devices. And in this case, what happens is we use the master key to set up a secure channel with your HSM. And then we will encrypt the database key using a cluster key that's only kept on the HSM. And so when the cluster starts up, it passes the encrypted database key to the HSM. HSM decrypts it, passes the decrypted key back to the cluster over a secure channel, and it's only kept in memory at that point. And then you have the block keys and proceed as normal. The other benefit of this multi-tier key approach is key rotation is only a matter of changing your database keys and cluster keys, and then we can re-encrypt the block keys. And so you maintain a secure chain, but you don't have to dump and re-encrypt all of your data. And so when you're dealing with hundreds of terabytes or petabytes of data in a system, having the ability to rotate without having to do a full dump and reload is a big plus. And it's possible to run these HSMs in HA fleets on-premise. And actually, if you go to there's a session at 4:30 where NASDAQ will talk about how they're using HSMs on-premise in an HA configuration with Redshift to encrypt their exchange data. And then encryption in Redshift is at the database level, so it's all on. And for customers that want to restrict access to certain columns, the strategy is to take views, put only a subset of columns in the views, and then assign permissions to the views, but not to the underlying tables. And that way you get column-level restriction within the cluster. So security is great, but you also want to control access, and you want auditability. And so with Redshift, you can require SSL. So any client applications will connect over SSL. We support ephemeral key exchange on the SSL handshake, so you get perfect forward security for that session. And then we have database permissions, so you can create users and assign users permissions to SQL and to database objects. And while object-level permissions are great, customers also wanted the ability to assign permissions at the schema level, and so we recently added the ability to grant or revoke permission to all the objects in the schema. Again, convenience for customers who are creating objects frequently or who are managing large user populations in the database. And then we integrate with VPC, which, as I'm sure all of you are familiar with, is our virtual private cloud, so you can isolate the cluster and connect it to your on-premise resources over VPN. And then we integrate with IAM at the resource level, so you can control who can take what action, like provisioning a cluster, creating a backup, resizing a cluster. And that's all available and auditable through CloudTrail, which is our API logging and auditing service. And then Redshift also provides database-level audit logging. And so the idea here is that you create a location on S3. You give us put permissions into that location, but not delete. And so we will just write database audit logs into that location for you to consume in another auditing application. And so it's connections, failed attempts to log in, what SQL was executed, really full SQL activity is logged out to S3 for your consumption. And so securing data is great. We've ingested data. Now we want to talk about query capabilities in Redshift. And so we've been iterating quickly. Andy talked about 95 new features. We add SQL functions regularly. We want to expand the range of analytics that you can do in SQL. We've added over 25 since launch, new aggregate and window functions, regex capabilities. And we're going to continue iterating here, but we also want to enable you to add your own functionality to Redshift. And so I'm excited to share with you that we'll soon have user-defined functions available. These are coming in a couple of weeks. And you'll be able to write your own functions in Redshift using Python 2.7. The syntax is largely identical to Postgres UDFs with PL Python. And there's a slight difference in that because Redshift is a distributed system, you have to provide a keyword around whether your function is immutable or stable or volatile, which is optional in Postgres, but required in Redshift. But if you're familiar with Postgres UDFs, this will seem like old hat. And we do sandbox these UDFs, so you can't make file system or network calls, but otherwise the full Python interpreter is available to you, and it runs as compiled bytecode in parallel on all of the compute nodes. And we're also going to build in some libraries, so Pandas, NumPy, and SciPy for analytics will be built in. Those functions are available to you for use. And you can also bring in your own libraries. So let's talk about how this will work. So a very common thing that our customers do is URL parsing. So you might have a refer string for your web traffic. You want to split it up. You want to get domain. You want to get keywords, where people came from. Now, if you're doing this in SQL prior to UDFs, you will be using a fairly complicated set of regexes to extract your domains. With UDFs, you'll just create a function. In that function, you can import Python's URL parsing library, and you can write a very simple function that will take data, return the host name, and you'll have to write multiple ones to give different aspects of the URL string. But it gives you a very elegant way to expand the capability of the database and bring it into your SQL queries. And we also support aggregate functions. So listag is a function that customers ask for a lot. The idea here is that you can combine multiple values into a single string and output it. It could be useful, say, for example, you're tracking visitors to your website and you want to have a list of all the sites that they came through in their attribution pipeline on their way to your site. And so with UDFs, you can create an aggregate function that will allow you to essentially replicate this behavior. And so aggregates in Redshift UDFs and Postgres UDFs have three components. There's an initialization function which sets it up, an aggregate function that does the actual aggregation, and then a finalize function that combines all the results and returns them to the application. So here you can see we've got an init listag. We've then got the aggregation itself, which concatenates the values with a comma. And then we've got a finalize, which just closes the list. And then the aggregate function is just defined where you provide pointers to these three individual UDFs that you've defined. And so if you wanted to use this in a query, here's a simple table and a create syntax. And then you can see that you can very elegantly bring that aggregation function into your SQL query and quickly get back the list ag result, summing by column B, is grouping by column B all of the values that were in column A. And so this is a very elegant way, again, to really expand the capabilities that are available within Redshift. You'll have this in a few weeks. We will continue iterating on built-in aggregate functions. Python bytecode will run as fast as possible, but it's not going to beat native C++ that's running optimized in the system. But we're excited to hear what you think about this, so please let us know. And with that, I'm going to turn over to Anurag, who's going to talk about space-filling curves.
Hey, so how many of you know what a space-filling curve is? A couple. Thanks a lot, Rahul, for giving me this section. So let's talk about this a little bit. So let's imagine your small internet bookstore. And you're interested in how you're doing, right? You've got a bunch of sales. You want to know your best customers. You want to know your total sales. You want to know which products are best. So that's actually a pretty easy problem, right? You build a star schema, and you stuff it into a database. You put some indexing on it, and away you go. You get a little bigger. Your queries start taking a long time. So something you'd start doing is moving to a column store. And what we do in Redshift, what a lot of people do, is use zone maps, which means that you keep the minimum and maximum value per block. And we have large data blocks, right? And it's relatively inefficient to index in a zone map. And the reason for that is that since you have a large block, let's say it's a megabyte block, as in Redshift. Now, each block is per column. Let's say you've got an integer column. You're looking at 250,000 values per block after compression. And for an index to be selective, you need it to be worth doing 2 IOs, the index IO plus the data block IO. So you need selectivity of 1 in 500,000. Most of you don't have that data. So you have to decide which queries you want to be fast. So the way you do that is you decide what you're going to sort on. So let's say you are trying to figure out products or customers. So if you sort on products, then the sorted columns are going to be log n. But the unsorted column, customer, is going to be order n. It's just going to do a full scan. That's if you don't specify both, right? And that's true even if you use a compound key. Because if it's product followed by customer, if you don't specify the product, there isn't enough selectivity to go through the customer list. Okay? Now, what other people have done, and is what's kind of state of the art nowadays, is to use projections. And that's just a fancy word for saying, we're going to go and store your data sorted multiple ways. And that way you can say, OK, sort it by product, sort it by customer, and choose which one you're going to use. But it gets unwieldy. The loads are a lot slower. And if you have, say, 8 columns that you might want to sort by, you've got 8 factorial combinations that you would want to create these sorting combinations on, because it's not just the one column that you're going to sort on, it's the combination, right? So a little math ahead. So one way that you can think about this problem is Hilbert spaces, or multidimensional spaces. You can think about each block existing at the intersection of a number of axes, which are the things you want to index on. And so what you see on the right-hand side there is something where you're basically sorting by customers first, then products. So for each customer, you see the list of products. And then the one below it is the opposite order. Now, it turns out that that's an over-specified problem. What we're doing there is, well, let's first introduce what a space-filling curve is. So what a space-filling curve is it's a curve that goes through the multidimensional space and touches every point. Okay? And so what you're doing here is a space-filling curve. You're going across each time, or you're going down each time, right? And that works just fine. But what I mean by it being over-specified is that you don't need every product to appear per customer. You just need every product, every product 2 to appear after every product 1. So that order preserves. You need every customer 2 to appear after every customer one. And there's a more efficient way of doing it. There are a ton of space-filling curves out there. This happens to be the one we're using. Sorry. The advantage of the one that we're using here is that you get to, in a two-dimensional model, go to something where if you're specifying both product and customer, you're going to be log n. If you're specifying either product or customer, you're going to be square root of n. If you specify neither product or customer, of course, you're going to have to do a scan. And that's a big deal, because what you're getting the ability to do now is by specifying a set of columns out of the list that you tend to query on, you're basically starting to get the benefits of indexing without the overhead of indexing. So with all that math, let's talk about how you use the feature. So basically, you're familiar with how you do a create table. And so you're familiar with how you specify a sort key. So you just specify a list of columns. The default way that you do that is what we're introducing a new keyword called compound. That's the default. You don't have to specify it. Your tables will work just fine. There's a new model, which is interleaved. That's the basic change that you're going to introduce if you want to use space-filling curves. And when you specify that, what we're going to do is interleave the bits that are used to specify your zone map. No changes are needed to your queries. We're seeing pretty good advantages from this, on the order of 4 to 8x in our lab. So we think the benefits are significant. Right now, we're still seeing a load penalty. We'll be fixing that quickly. As with UDFs, should be available in a few weeks. Love to see your feedback on it.
And, we wanted to leave lots of room here for questions. Happy to take any questions that have come up as a result of this, or any topics that we haven't covered, since all of you are fairly advanced users from a Redshift perspective. And if not, you're welcome to have some extra time back in your day. Yep, go ahead. It's unclear. It will probably feel significant based on the complexity of the kind of processing that you're trying to do. They definitely won't run as fast as native UDFs. So it'll be an area that we're consistently tuning. I don't know if we have more specifics on that.
Yeah, I mean, I think I would estimate it being not that different from Postgres, which I would say that it's on the order of magnitude, right? Because if you think about it in Redshift, we compile down to C++ and turn it into machine code every query. And so the native queries, native functions run pretty fast. Whereas Postgres, you just can't, with Python, you just can't do that.
Go ahead.
How do you do the compute node crash recovery when the node crashes? How do you do that? And secondly,
Sure. The question, just to repeat it, is around how we handle crash recovery on the compute nodes and what do we do for backups. So whenever you load data into a Redshift cluster in a multi-node system, we actually automatically replicate it to other drives on different nodes. And then we are also continuously backing up all of the compute nodes and the leader node to S3. So anytime there's 5 gigabytes of new data or 8 hours have elapsed, we take an incremental S3 snapshot of that compute node. But we maintain a full chain going back of the snapshot itself, so we can recreate the complete status of that compute node at any point in time. And you get to pick the retention period of these automatic S3 snapshots. 1 day is default. You can have up to 35 days. And you can also choose to have those S3 snapshots copied to a second region to get global DR. And so if there is a compute node failure, essentially our systems will detect it. We then have the opportunity to try and restart the node if that's possible, because if you have up to 16 terabytes of compressed data on that node, it can be quicker to restart it than to replace it. But then if we do need to replace the node, it's not a problem, because we have all the blocks on that node saved not just on S3, but also on other drives, the secondary copies that are also in the cluster. And so we can replace the node automatically, reconnect it to the cluster, and then we will allow you to resume querying within a few minutes. It takes under 3 minutes to provision a node, at a minute or so to load metadata back onto it. And then we will replicate data back onto that node from the other nodes in the cluster. And so you can resume querying as soon as that's available. If the entire cluster needs to be restored, you can push button and restore from snapshot, and we will stand up an identical cluster, and then we'll begin streaming data back into that cluster from S3. You can query that cluster as soon as it's available. Same idea, 3 minutes to provisioning, another minute or so for metadata, and then begin querying. And then our streaming restore feature will stream back blocks into the cluster as you query. And because most customers tend to have a locality of reference in time, so by that I mean, say at Amazon, when we're looking at our data, we tend to focus a lot more on today and yesterday and this week and this month, much more so than what happened 18 months ago. And so because of that locality of reference, those blocks come back much more quickly. And so normal operational performance is achieved much more quickly once just a subset of that data is back on the cluster. If drive fails, we can handle that automatically because we have copies of the data in cluster, and we have spare space on the nodes. We actually reserve almost 2x the capacity as a spare space so we can rebuild drives that were lost without having a really significant impact on the cluster itself, and queries will automatically get resubmitted if they were impacted by that. Does that answer the question?
Yeah. A simple way of thinking about it is it's basically page faulting. We're page faulting from S3 if we don't have data.
So I put some solutions there about design, and the common is to integrate the final size schema and the data model using CI. Having the setup, the context of the API chain, the source schema to state, then you get a good shot. What are the best practices in terms of what data architecture? Or you go to your production relationship up to the columnar store and the size schema, and giving the challenge of the
So we have customers that, so let me just repeat the question. So the question is, are there best practices from going from a transactional schema into a data warehouse optimized star schema in a column store? And there are a number of ways you can do it. So we've designed Redshift to be flexible and performant, whether you're running third normal form or star schema or fully denormalized. It's really up to you. And we have customers that will do a number of things. They might do a traditional ELT process where they will extract the data, load the data into Redshift, and then transform it in cluster using SQL. And then now with UDFs, you'll have a bit more capability to do some of that processing. But you could also do a traditional ETL process where you will extract from your OLTP stores. You might be able to use technologies from our partners like Informatica or Tunity that will do extract and transformation and then load into Redshift. It's pretty common to load into a staging table in Redshift and then use a series of join operations to essentially merge into your main fact tables. And the other approach, though, is also just to bring the data in as you generate it. So in the case of log files, customers will sometimes just load them as they are and then process them once they're in database. So it's really around adapting to the tool chain that you have and making that work. I'd say the vast majority of our customers use the copy mechanism because it's the highest and best performant way to bring data into Redshift. And the staging table pattern is also relatively common simply because Redshift doesn't support a merge directly, so you end up doing an upsert workflow where you load into staging, join into main, and then add in the new records. Does that answer your question?
Okay. I'll just add a couple of thoughts there. One is a number of our customers use EMR as a way of doing transformations, and we think Hadoop is a great way of dealing with transient flows, not a cluster that you're going to keep up all the time, but EMR is a great place to just stand something up, push data through, run some custom logic on it, and then push it over. So a lot of people do that. The other hint I might give you is that one way to think about a difference in a columnar data warehouse is that there's nowhere near the penalty in having big rows, right? And so a lot of people use that opportunity to do further denormalization than they might do otherwise, and just say, rather than having something be in separate dimension that they have to join, to remove that join and just put those columns directly into the table itself, because the I/O penalty is nowhere near as great. Make sense?
Actually, that brings up one other point, which is when you're designing your schemas, thinking about what you're going to join can also be a big factor, and so thinking about distribution keys to co-locate joins, and the ability to distribute dimension tables to all of the slices using the dist style all. That's another way to get some more performance out of that final schema.
That's an interesting one.
Favorite CloudWatch metrics. So we publish things like disk space utilization, CPU utilization, network bandwidth. We definitely recommend having alarms on disk, on the amount of disk that's being used. And beyond that, I think there's richer metrics actually at the system table level in the cluster. So we provide a lot of metrics on query execution, which step in the query you're at, how long each step took, is there queuing? A lot of that's available in system tables and design.
There's some neat functionality coming there in the console in a few weeks as well.
Yeah, we will provide some more ways to get at what's actually happening from an execution perspective at every level of the query.
Recently migrated from Uniqueness into Redshift, and I'm super psyched that you guys built in UDFs and Python to it. So thank you for that.
Great.
Super excited about that. The question is, earlier in the security section, you detailed the client-side encryption methods. Any reason you didn't kind of talk through server-side encryption? Would that be another alternative, or is there some reason?
Thank you for the feedback on UDFs. We're glad you're excited about it. And the question is around, is there a reason we didn't go into detail on server-side encryption? No particular reason other than it's just transparent. So if you have server-side encryption enabled buckets or objects on S3, Redshift can just copy from them since it's transparent to the cluster, because S3 handles that encryption and decryption on access of the object. So I just didn't go into it because from the perspective of using Redshift, it doesn't really matter, because you're just going to copy, point to an S3 location, and S3 will take care of encryption and decryption at that level. We did tweak the unload command recently, so you can now unload data from Redshift, and unload is essentially the inverse of copy, so you can run arbitrary SQL and run a parallel extract onto S3, and that can now be done to SSE-enabled buckets, so you can have server-side encryption enabled by default. Or we also built in client-side encryption on extract, so you can provide a private key, and we'll then use that to do envelope encryption of the extracted data. Yes? So that, I will definitely take that requirement. You're talking to the right people. So unload today is a flat file. Essentially, it will come out in delimited format. You get to pick the delimiter that it comes out in. But I'd love to, please follow up with me, and we'll be happy to get into the details of the unload with JSON use case. Yes, sir? Sorry, I missed that. Sure. So the question is there a plan to include sorting as part of the copy command? So actually, the copy sorts your data automatically. The sort key is defined at the table level. So when you're setting up DML, you would actually define columns as your sort key columns. And in that case, the copy will just sort your data as it comes in. So there's no further action you need to take from a sort perspective. One nuance there is that we recommend, if you can, to load data. Say you have a sort key based on date. If you load data for Monday and then load data for Tuesday and then for Wednesday, essentially your table will load sorted. And your vacuum operation will be very fast because your data is already sorted. Whereas if you loaded Monday, then Wednesday, then Tuesday, each individual day would be sorted, but you'd still have a section of the table that was out of order, and so your vacuum would have to reshuffle.
That said, we're reducing the penalty on that.
Yeah.
In addition to all the features we push out, there are, there's almost twice as much work that's going on internal stuff.
No, that's great. That's true. Yep. So we can't comment on our roadmap beyond the things that we've talked about, but I would say the notion of supporting some form of filtering on copy is one that a lot of our customers have asked us about, and customer feedback is definitely something we take pretty seriously. So completely understand the value and the utility of that request.
If there's a specific use case there, just talk to him. We'll make sure that if and when we do it, we cover it.
Yes, sir, in the back there. Yeah, so concurrency, the question is around plan around concurrency. So earlier this year, we upped from 15 concurrent query slots to 50 concurrent query slots. From a columnar database perspective, there's a fundamental philosophical difference behind a column store and a row store. With a column store, your goal is to apply as many resources as possible, as quickly as possible, to get answers to complex queries quicker. This is different from a row-based database where you're trying to do lots of smaller operations typically. So our main investments around concurrency and the way customers work with concurrency is good use of workload management queues. So we have the ability to let you define queues, assign slots and memory to those queues, and so you can ensure that you have resources available for basically ensuring that batch and heavy jobs get done, as well as having space for point queries. But in general, to Anurag's point, I think improvements at the subsystem level around performance, reliability, availability, those will always be ongoing. Yes, sir? So I can start, and Anurag, you can also add to this one. So, our fundamental philosophy around database services is that one size doesn't fit all, and so, Aurora is a high-performance transactional database, and Anurag can definitely talk to that. I do imagine that there will be some use cases where people ran out of headroom on vanilla MySQL and perhaps moved to Redshift for that. That would be well served with Aurora, but I suspect there are also still reporting use cases where large scans fundamentally aren't going to be a great fit for an OLTP optimized system. But yeah, I fully expect customers will make the choice that's best for their workloads.
Yeah, I think that's exactly right. I mean, we really believe one size doesn't fit all. Aurora is really oriented towards OLTP workloads. So to the degree that you were getting, you would have thought about MySQL or Postgres before thinking about Redshift, or there's overlap there. There probably continues to be overlap with Aurora. There's probably a little bit more overlap because we go up to 64 terabytes of space, which is a fair bit bigger than the largest databases that are available in RDS through the traditional systems. But that's still small from a Redshift perspective.
Yep. Go ahead. Sorry, just behind you, one second. Yeah, so the leader node actually isn't a bottleneck from a concurrency standpoint. It's really just coordinating the query execution. So if you look at your cluster graphs of CPU utilization, for example, in the console, you'll find the leader node barely does any work. It's really a fundamental process model around columnar databases and how those operate. And so the best strategies for concurrency are good workload management. But the other piece is there is no penalty in Redshift to having multiple clusters. So if you had 10 nodes in a single cluster or 10 one-node clusters, that would be a way that some of our customers have essentially been able to scale up concurrency and scale wide when they've needed to. The other piece is from a data warehousing perspective, you typically will have some form of analytic layer or a BI or visualization layer, and that can also help handle the concurrency and scale out if you're running large populations accessing that data.
The only thing I'll add to that is that we're aware that there's pain that you guys have around concurrency, and we're thinking about it.
The question is around copy and movement of data between two Redshift clusters. So again, I cannot comment on specifics. I think that use case and in general desire for more flexibility around copy is an area that we're aware of. Today, customers that are moving data between Redshift clusters essentially use unload and copy semantics together in order to do that. Go ahead.
Expanding on the previous answer to this question about Aurora. So, and I think when I think about the high-volume data warehouse and going from the source to the target architecture schema, I still see a challenge, right? If you need like the traditional data warehouse support like data lineage, so going EMR as well, maybe it's a challenge.
Mm-hmm.
At the same time, trying to do all that state high volume work inside Redshift may be performance impact. So on the Aurora
Possibly. I guess my thinking would be, I mean, I'm not sure I understand in depth what you're saying, but we can talk offline. But my thinking would be that data transformation is one of those embarrassingly parallel problems. And so therefore, it actually lends itself towards a system like Redshift, which can run a large query over a lot of nodes, or a system like Hadoop, where you can spin up a lot of nodes, run your operations. And so in that case, I'd have loaded to a staging table in Redshift and done the transformation in an ELT chain, or I would have used Hadoop and done more complex transformations across a large cluster that maybe was only up for half an hour. But I'd probably do that rather than having a singular node kind of system which is acting as a throughput part of the chain. I mean, that's just my bias. I don't know whether it's appropriate.
Go ahead.
Aggregate UDFs, they also operate
So that is different. At the moment we support scalar and aggregates. You can essentially, you'd have to run multiple UDFs in SQL to get table type functionality.
Back.
So, today in Redshift, you can actually store JSON, and there are built-ins that let you access that. But in terms of other data formats, the way we think about it is AWS as a data platform is actually a really excellent one. You've got streaming support, you've got NoSQL support, you've got EMR, and you've got Redshift, all underpinned with S3, which is a common way to move data between all of these services. And so to date, those have been the ways that customers have been accessing all of that data. And we often see analytic applications that span multiple services for that reason. The other benefit to keeping these things in sort of a service model that connect together is that you can use as little or as much of each one as your use cases dictate. And so can build pretty sophisticated analytic application topologies that way.
Yeah. The thing I'd add there is, I think you're right that it's an emergent use case. It's just a question of, to me, whether the right model is to support nested data directly in the data warehouse or to transform it into a relational model so that traditional relational tools have more accessibility to it. Because the sort of technologies you're talking about aren't really consumable if you want to use tools. They're consumable if you want to use SQL variants that are custom to that particular engine. So, that's the debate that I think is ongoing in the industry right now.
Sir? I'm sorry, I couldn't hear that at all. Again, we can't comment on specifics. I think that the things that we can say are with UDFs, you will be able to write and persist really any functions that you can write in Python in database. And then we will continue iterating on the SQL functionality side. I think if there's specific functionality that you're interested in that isn't covered by each of those use cases, I'd love to hear about it, and we'd appreciate the feedback and input on that side. Oh, yeah.
From Dynamo to Redshift, is there a plan to support micro batch and
So we have, Dynamo announced a preview of Dynamo Streams, and we're working on integrations with Dynamo Streams into Redshift, and so that should support more of the continuous update use case in that area. I think it was discussed, so we're working on that piece of it. So Redshift backed into Dynamo. So, actually, I've heard about this request in a couple of cases, and to date, customers are using custom applications to extract data from Redshift. I'd love to learn a bit more about your use case on that front. I suspect I have an inkling of what it's related to, but it would be good to get some details. And, in general, the way we like to build products is We really want to hear from our customers about the things that they want to do but cannot, because it gives us a real opportunity to work and to prioritize our efforts so we're building the things that our customers really care about. And I think we're
that's everything.
Out of time here. So thank you very much for coming. Really appreciate it. And we'll be around.